The light touching your eyes tonight may have crossed millions of years of darkness to reach you, and the gravity holding you to your bed is quietly bending the fabric of the universe itself. Space physics is not abstract theory, it is the rule book of reality. In this journey through 100 true facts, you'll discover how light sets the speed limit of existence, how time can stretch and slow, how stars forge the atoms inside you, and how the cosmos is still expanding. Stay with me. The universe is about to reveal how deeply you belong to it. Light travels at 186,282 miles per second in the vacuum of space, and this is not merely a fast speed, it is the absolute upper limit of how quickly anything in the known universe can move. Nothing with mass can reach it. Nothing with mass can even approach it without requiring more and more energy, endlessly, until the math becomes impossible. It is a ceiling built into the structure of reality itself, a quiet law that everything in existence obeys without exception. When you lie still in the dark and think about that number, 186,282 miles in a single second, it begins to feel less like a fact and more like a kind of music. The light coming through your window right now, the soft glow of a distant street lamp or the pale silver of moonlight, has been moving at that exact speed since the moment it was born. It has never slowed down. It has never needed to rest. And now, after all that traveling, it has found you here, lying quietly, breathing, drifting slowly toward the edge of sleep. The light that touches your skin on a warm afternoon is not fresh. By the time it reaches you, it is already 8 minutes and 20 seconds old, born at the surface of the sun at a moment that has already passed before you ever felt its warmth. The sun is approximately 93 million miles away from Earth, and even at 186,282 miles per second, light needs that full 8 minutes to cross the distance. This means that when you look up at the sun, carefully, briefly, you are not seeing the sun as it is right now, you are seeing it as it was 8 minutes ago. In those 8 minutes, the sun has continued to burn, continued to fuse hydrogen into helium, continued its patient and ancient work. But that particular light, the light falling on your face at this very moment, left home before you even noticed the sky. It traveled all that distance just to find you here, warm and still on the edge of sleep. Visible light, the rainbow of colors that human eyes can detect, is only a vanishingly small portion of the full electromagnetic spectrum. The universe is filled in every direction with forms of light that our eyes cannot see at all. Radio waves drifting through walls and bodies without a whisper, infrared light glowing warmly from every living thing, ultraviolet light just beyond the violet edge of a rainbow, X-rays dense enough to pass through flesh and illuminate bone, and gamma rays born in the hearts of exploding stars carrying more energy in a single wave than most things can hold. All of these are light. They are all the same phenomenon, differing only in wavelength and energy. And all of them are passing through you right now, invisibly, silently, as they have been your entire life. The universe speaks in frequencies your eyes were never built to hear, and it has been speaking constantly and without pause since long before you arrived. Radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays and gamma rays are all simply different expressions of the same underlying phenomenon, the electromagnetic wave. What separates them is nothing more than the distance between one wave peak and the next, a measurement called wavelength. Radio waves can have wavelengths longer than a building. Gamma rays have wavelengths smaller than the nucleus of an atom. And yet they are all, at their core, made of the same thing, oscillating electric and magnetic fields rippling outward through space at the speed of light. The universe does not see these divisions the way we do. It does not distinguish between the radio signal carrying a song and the X-ray passing through a chest. To the cosmos, these are all simply light, traveling in every direction, carrying information about the things that made them. Tonight, while you sleep, all of it will continue, quiet and unstoppable, filling the dark with invisible conversation. When you look at the Andromeda Galaxy on a clear, dark night, a faint smudge just barely visible to the naked eye, you are not seeing it as it is. You are seeing it as it was 2.537 million years ago, because that is how long its light has taken to cross the distance between that galaxy and your eyes. In that span of time, our ancestors were early humans, walking upright across the African continent, looking up at that same galaxy and seeing light that had left even earlier. Light is a kind of time machine, and every object in the night sky is a window into the past. The farther away something is, the older the light that reaches us. Astronomers who study the most distant galaxies are not seeing the present universe at all. They are archaeologists of light, reading the ancient story of a cosmos that looked very different from the one we inhabit now. And all of it, all that ancient travelling light, began its journey long before any human thought to look up and wonder. From the perspective of a photon, a single particle of light, there is no journey, there is no travel time, there is no crossing of vast distances over millions of years. According to Einstein's special theory of relativity, a particle moving at the speed of light experiences zero passage of time. The moment of its creation and the moment of its absorption are, from its own frame of reference, identical, a single, timeless instant. The photon that left a distant star 1 billion years ago and arrived at your eye tonight did not experience that billion years. It simply was there, and then it was here, with nothing in between. Time, as we experience it, as the slow turning of hours and the accumulation of days, is a feature of things that move more slowly than light. The universe's most fundamental messenger exists outside of time entirely, and every ray of light that has ever warmed your face has arrived from its own point of view, the very instant it was born. The cosmic microwave background radiation is the oldest light in the observable universe. A faint and almost imperceptibly gentle glow that fills the entire sky in every direction, left over from a moment 380,000 years after the Big Bang. Before that time, the universe was so hot and dense that light could not travel freely. Matter and energy were tangled together in an opaque, luminous fog. Then, as the universe cooled, electrons and protons settled into neutral atoms, and the fog cleared, releasing a flood of light that has been traveling ever since. That light has been stretched by the expansion of space until it now falls in the microwave range, invisible to the eye but detectable with the right instruments. It is the universe's oldest memory, a soft and ancient warmth that permeates all of space, the fading echo of a moment when everything was young and bright and impossibly close together. And it is here with you now, tonight, as you rest. When white light enters a glass prism, something gentle and wonderful happens. The different wavelengths of light, each corresponding to a different color, slow down by slightly different amounts as they pass through the glass, and because each one slows by a different degree, each one bends at a slightly different angle. Violet light bends most, red light bends least, and all the colors in between arrange themselves in the precise, luminous order of the rainbow. Red, orange, yellow, green, blue, indigo, violet. What this means is that white light, the ordinary, seemingly colorless light of the sun, has always contained every color within it, hidden and waiting for something to spread them apart. A prism does not add color to light. It reveals what was always there. The same process happens when sunlight enters a raindrop, which is why a rainbow appears after rain. The sky is simply reminding you that ordinary things looked at in the right way are full of hidden and extraordinary beauty. Stars are not all the same color, even though from a distance they may all look like simple points of white light. Look carefully on a clear night and you will notice the faint differences. This one a cooler red, that one a brighter blue-white, another one a warm and steady yellow. These colors are not decorative. They are direct measurements of surface temperature, read by the eye across millions of miles of space. Blue and blue-white stars are the hottest, burning at surface temperatures above 25,000 degrees Fahrenheit. Red and orange stars are the coolest, burning at temperatures closer to 5,000 or 6,000 degrees Fahrenheit. Our own sun is a comfortable middle temperature, a yellow-white star burning at about 10,000 degrees at its surface. By simply looking at the color of a star, astronomers can know its temperature instantly, as easily as reading a number on a dial. The night sky is not a scattering of identical lights. It is a display of 1,000 different temperatures, burning in 1,000 different shades. Gravity, as most of us learned it, is a force, an invisible pull that the Earth exerts on everything around it, holding us to the ground and keeping the Moon in its orbit. But Einstein, in 1915, offered a more complete and deeply beautiful picture. Gravity, he said, is not a force at all. It is the curvature of space-time, the four-dimensional fabric of the universe, caused by the presence of mass and energy. When a massive object like Earth or the Sun exists in space-time, it warps the space around it, the way a heavy ball placed on a stretched rubber sheet creates a depression. Other objects, planets, moons, comets, even light, then follow the curves in that warped space, and what we perceive as gravitational attraction is simply objects following the natural geometry of the space they inhabit. The Moon does not orbit the Earth because the Earth is pulling it. The Moon follows a curve in space-time that the Earth's mass has created, and that curve happens to be a nearly circular path. It is less like a tug and more like a dance, choreographed by the shape of space itself. Every object with mass, every planet, every star, every galaxy, every grain of sand, warps the space-time around it, creating a gentle curvature that radiates outward in all directions. The more massive the object, the deeper and wider its warp. The Sun, containing 99.86% of all the mass in our solar system, creates a space-time depression deep enough to hold 8 planets and countless smaller bodies in stable orbits for billions of years. The Earth creates a smaller but still significant curvature, enough to hold the Moon in a gentle loop that has remained almost unchanged for over 4 billion years. Even you, sitting or lying still right now, create a tiny and immeasurably small warping of space-time around your body, too faint to detect with any instrument, but real nonetheless. Every atom in the universe is bending space in its own quiet way, contributing to the grand and intricate geometry of a cosmos that has been folding and curving around mass since the very first moments after the Big Bang. Time does not pass at the same rate everywhere in the universe. In a stronger gravitational field, closer to a massive object, deeper in a space-time curve, time moves more slowly. This is not a metaphor or an approximation. It is a physical reality, measured with extraordinary precision and confirmed by decades of experiment. A clock placed on Earth's surface where gravity is slightly stronger runs fractionally slower than an identical clock placed on a mountaintop where gravity is slightly weaker. The difference is tiny, a matter of nanoseconds over long periods. But it is real, and it accumulates. Astronauts in orbit age very slightly faster than people on Earth's surface because they are higher in Earth's gravitational field and time moves a tiny bit quicker there. Near a neutron star or a black hole where gravity is incomparably stronger, time slows dramatically. Deep enough in a gravitational well, time would seem almost to stop, stretching moments into something that has no name in ordinary human experience. The GPS satellites orbiting Earth are in a constant, gentle battle with time. Because they orbit at high altitude, where Earth's gravitational field is weaker, time moves slightly faster for them than it does for a clock on the ground, about 45 microseconds faster per day. But because they are also moving at high orbital speeds, the time dilation of special relativity acts in the opposite direction, slowing their clocks by about 7 microseconds per day. The net effect is that GPS satellite clocks run approximately 38 microseconds fast every single day relative to clocks on Earth's surface. That sounds like an insignificant amount. But GPS works by precisely timing the travel of radio signals, and at the speed of light, 38 microseconds of error translates to roughly 7 miles of positional error accumulating every single day. Engineers account for this relativistic correction in the design of every GPS satellite. Einstein's equations written over a century ago are quietly embedded in the technology that tells you how to get home tonight. In September of 2015, for the first time in history, 2 black holes collided 1.3 billion light-years away, and the ripple from that collision reached Earth. Not as light, not as sound, but as gravitational waves, literal ripples in the fabric of space-time itself, predicted by Einstein in 1916 but never directly detected until that moment. The LIGO detector, a remarkable instrument consisting of 2 tunnels, 4 kilometers long arranged in an L shape, detected the wave as it passed through Earth. The tunnels changed length by less than 1,000th the diameter of a proton. That is how sensitive the instrument had to be to catch a ripple that had traveled 1.3 billion light-years and arrived here as the gentlest of whispers. The universe had been sending these ripples for billions of years through every collision and cataclysm, and they had been passing through us undetected our entire existence. Now we know they are there, flowing through everything, silent messages from the most violent events in the cosmos. A black hole's event horizon is not a physical surface. There is no wall there, no visible boundary, nothing you could touch or see as you approached it. It is simply a location in space, a threshold, a point of no return, defined entirely by gravity. Inside the event horizon, the gravitational pull is so extreme that the escape velocity exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing inside the event horizon can ever get out. Not matter, not signals, not light itself. The event horizon is the universe's ultimate one-way door. Information that crosses it is, for all practical purposes, gone from the observable universe. The word horizon is well chosen, just as the visual horizon of a landscape marks the farthest you can see. The event horizon of a black hole marks the farthest that any signal can travel outward. Beyond that line, the universe keeps its deepest secrets. Every day, twice a day, the oceans of the world rise and fall in response to the gravitational pull of the moon. The side of Earth closest to the moon is pulled toward it slightly more than the center of the Earth, and so the ocean there bulges outward in a gentle swell. The side of Earth farthest from the moon is pulled slightly less, and so the ocean there bulges outward in the opposite direction away from the moon due to inertia. Earth rotates beneath both bulges once each day, and as it does, most coastal locations experience 2 high tides and 2 low tides every 24 hours. The sun also contributes to tides, though its effect is only about half as strong as the moon's despite the sun's vastly greater mass, because tides depend on the difference in gravitational pull across the diameter of the Earth, and the moon, being so much closer, creates a larger difference. The tides you hear at the shore, the rhythm of the water rising and retreating, are the ocean's quiet reply to the gravity of the moon, a conversation that has been going on for billions of years. At the center of a black hole, according to the equations of general relativity, lies a singularity, a point of theoretically infinite density where the known laws of physics break down entirely and cease to offer meaningful predictions. The matter that has fallen into the black hole is believed to be compressed into this point, a location in space-time where curvature becomes infinite and the familiar concepts of space, time, and physical law lose their meaning. Most physicists believe that the singularity is not a real physical object, but rather a sign that our current theories are incomplete, that a more comprehensive theory of physics, one that unifies general relativity with quantum mechanics, would replace the singularity with something less infinite and more describable. What actually exists at the center of a black hole remains genuinely unknown. It is one of the honest edges of human knowledge, a place where our most powerful tools for understanding the universe go quiet, and we are left standing at the boundary of what can currently be known. When a massive star exhausts its fuel and collapses, the result can be a neutron star, an object so extraordinarily dense that the mind struggles to find a way to hold the scale of it. A neutron star typically contains between 1 and 2 times the mass of the Sun, compressed into a sphere only about 12 to 15 miles across, roughly the size of a city. At that density, a single teaspoon of neutron star material would weigh approximately 1 billion tons on Earth, roughly the weight of Mount Everest compressed into a space smaller than a sugar cube. This density is possible because in a neutron star, the normal atomic structure that keeps matter from collapsing has been overwhelmed. The electrons and protons that make up ordinary atoms have been crushed together into neutrons, packed so tightly that only the quantum mechanical resistance of neutrons to being in the same place prevents the star from collapsing further. The result is an object harder than anything in our ordinary experience, a city-sized sphere of almost pure neutrons spinning in the dark. Einstein published his general theory of relativity in 1915. And in the more than 100 years since, it has been subjected to an extraordinary number of precise experimental tests, and it has passed every single one. The bending of light around the Sun, first confirmed during a solar eclipse in 1919. The advance of Mercury's orbit, which Newton's gravity could not explain but Einstein's could. The slowing of clocks in gravitational fields, measured with atomic clocks on airplanes. The existence of black holes, predicted by the theory and now observed directly. Gravitational waves, predicted in 1916 and finally detected in 2015. GPS systems, which require relativistic corrections to work. Each new test is a chance for the theory to fail, and each time it holds. This does not mean it is the final word. Physicists know that general relativity and quantum mechanics cannot both be entirely correct as currently formulated, but it means that whatever comes next will have to agree with Einstein's equations wherever they have been tested. He described the geometry of the universe, and the universe has been agreeing with him ever since. Stars are not made in an instant. They form over millions of years, inside vast and slowly contracting clouds of gas and dust called nebulae. The word is Latin for clouds, and the name is fitting. These clouds, composed mostly of hydrogen and helium with traces of heavier elements, drift through the galaxy in enormous, loosely organized masses that can span hundreds of light years. In some regions, a disturbance, a shockwave from a nearby supernova or the gravitational tug of a passing cloud, causes part of the nebula to begin collapsing inward. As it collapses, it heats up. As it heats up, it begins to glow. Gradually, at the core of the collapsing cloud, pressure and temperature rise until they reach the point where hydrogen nuclei can be forced close enough together to fuse, a threshold of approximately 27 million degrees Fahrenheit. At that moment, nuclear fusion ignites and a star is born. The rest of the cloud may go on to form planets, moons, asteroids, and comets, a whole solar system assembled from the same gas and dust that gave birth to its star. Every second of every day, the sun converts approximately 620 million metric tons of hydrogen into helium through nuclear fusion. This is not burning in the chemical sense. No oxygen is required, no combustion is taking place. It is a nuclear process, occurring deep in the sun's core, where temperatures reach 27 million degrees Fahrenheit and pressures are almost incomprehensibly high. In fusion, 4 hydrogen nuclei are forced together to form a single helium nucleus, and in the process, a small amount of mass is converted directly into energy, according to Einstein's equation E equals mc squared. That small amount of mass, about 4 million metric tons per second, the difference between the mass of 4 hydrogen nuclei and 1 helium nucleus, is converted into energy with a ferocity that lights up the solar system. This process has been going on for 4.6 billion years, and it will continue for approximately 5 billion more. The warmth on your face on a sunny afternoon is the distant echo of nuclear fusion happening 93 million miles away every moment without pause. Our Sun is approximately 4.6 billion years old, which places it comfortably in middle age for a star of its type. It formed from a collapsing cloud of gas and dust in what is now the Milky Way galaxy, and it has been steadily fusing hydrogen into helium in its core ever since. Astronomers estimate it has consumed roughly half of the hydrogen fuel in its core and has approximately 5 billion years remaining before that fuel runs low enough to trigger significant changes in its structure. 5 billion years is a span of time that resists comprehension. The entire history of complex life on Earth represents less than 0.1% of the Sun's remaining lifetime. Civilizations rise and fall in the blink of an eye by stellar standards. The Sun will still be burning when the continents of Earth have shifted into configurations no map has ever shown, when ice ages and warming periods have come and gone countless times, when everything humans have built and thought and dreamed has long since dissolved back into dust and memory. The most massive stars in the universe are also the most extravagant and the most short-lived. A star 20 or 30 times more massive than our Sun does not live longer because of its greater supply of fuel. It lives far shorter, burning through that fuel at a rate so immense that it can exhaust a supply of hydrogen in just a few million years compared to the Sun's 10 billion year lifespan. This is because the internal pressure required to support such a massive star against its own gravity is enormous, and that pressure can only be supplied by a correspondingly enormous rate of nuclear fusion. The result is a star that burns with a luminosity hundreds of thousands of times greater than the Sun, blazing blue-white, visible from astonishing distances, pouring its energy into the galaxy at a rate that cannot be sustained. These brilliant, profligate stars live hard and die young in cosmic terms, lasting only a millionth of the time that a small, modest red dwarf star might survive. In the universe's long story, they are brilliant but brief illuminations. When a massive star reaches the end of its life and its core collapses, the explosion that follows is among the most violent events in the observable universe. A supernova can briefly outshine an entire galaxy of hundreds of billions of stars, releasing more energy in a few seconds than the Sun will emit over its entire 10 billion-year lifetime. The outer layers of the star are blasted outward in an expanding shell of gas and debris that can spread across dozens of light years, seeding the surrounding space with elements forged in the star's interior. These remnant clouds glow for thousands of years, luminous and slowly expanding, one of the most beautiful structures in the cosmos. Supernovae also trigger the formation of new stars, their shock waves rippling through nearby clouds of gas and dust, compressing them, initiating the slow collapse that will eventually birth new suns. Death, in this way, is also a beginning. The universe recycles its matter through these tremendous events, generation after generation, in a cycle that has been turning since the first stars ignited. The oxygen you breathe, the calcium in your bones, the iron in your blood, the carbon in every cell of your body, none of these elements were present when the universe began. The Big Bang produced only hydrogen, helium, and traces of lithium. Every element heavier than these, every element that makes up the complex chemistry of living things, was forged inside a star, or in the extraordinary violence of a supernova explosion, or in the collision of neutron stars. The gold in jewelry and the silver on cutlery, the phosphorus in DNA and the iron in red blood cells, all of it was assembled inside stars that lived and died long before our sun was born, scattered into space by stellar winds and supernova shockwaves, eventually gathered into the cloud of gas and dust that formed our solar system. You are not merely connected to the stars in a poetic sense. You are literally assembled from elements that were cooked in stellar cores billions of years ago and scattered across the galaxy before finding their way to you. When a massive star exhausts its fuel and undergoes a supernova, it does not simply vanish. What it leaves behind depends on how massive it was to begin with. A star between roughly 8 and 20 times the mass of the Sun will leave behind a neutron star. That extraordinary, dense remnant of crushed neutrons, only a few miles across but containing more than a solar mass of material. A star more massive than roughly 20 to 25 times the Sun will leave behind something even more extreme. A black hole, a region of space-time where gravity has overwhelmed all other forces and nothing can escape. Both of these objects are formed in the same event, the violent collapse of a stellar core, but they represent vastly different endpoints governed by the amount of mass involved. The line between becoming a neutron star and becoming a black hole is not perfectly defined and is still a subject of ongoing research. What is certain is that nothing is truly lost. The mass of the star lives on, transformed almost beyond recognition in one of the universe's most extraordinary structures. Some neutron stars, formed in the collapse and explosion of massive stars, are born spinning at extraordinary rates. As they spin, they emit narrow beams of radio waves from their magnetic poles, like cosmic lighthouses sweeping their beams across the galaxy. When one of these beams happens to point toward Earth with each rotation, we detect a pulse of radio waves arriving with almost clock-like regularity. These are pulsars, and their regularity is extraordinary, some of the most stable natural clocks in the known universe, losing less than a microsecond per year. When the first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, the signal was so regular and so unexpected that for a brief time it was nicknamed LGM1 for Little Green Men, a half-joking acknowledgement that no one could immediately think of a natural explanation for something that regular. The natural explanation, once understood, turned out to be even more wonderful, a collapsed star the size of a city, spinning hundreds of times per second, sweeping its beam across the dark. For many years, astronomers considered UY Scuti, a red supergiant in the constellation Scutum, to be the largest known star, with a radius estimated at roughly 1,700 times that of the Sun. But more recent measurements and discoveries have complicated that picture. Stephenson 218, a red supergiant located near the star cluster Stephenson 2, has emerged as a compelling candidate for the title of the largest known star, with estimates placing its radius at approximately 2,150 times the diameter of the Sun. To imagine that scale, if Stephenson 218 were placed at the center of our solar system in place of the Sun, its surface would extend beyond the orbit of Saturn. The precision of these measurements is limited by the immense distances involved and the behavior of the star's extended outer atmospheres, and the record may change again as observational techniques improve. What is clear is that the universe contains stars of a scale so vast that comparisons with anything in everyday human experience become almost meaningless. They are simply enormous beyond easy imagination. Red dwarf stars are the smallest, dimmest, coolest, and by far the most common type of star in the Milky Way. They make up an estimated 70 to 75% of all the stars in our galaxy, and yet not a single one of them is visible to the naked eye from Earth. They are simply too faint, but what they lack in brilliance they more than compensate for in longevity. Because they are so small, the gravitational pressure at their cores is modest by stellar standards, and they fuse hydrogen at a slow and measured pace that stretches their lifetimes into the trillions of years. The oldest red dwarfs currently in existence have been burning since near the beginning of the universe, 13.8 billion years ago, and they still have trillions of years left ahead of them. For context, the current age of the universe is not yet long enough for a single red dwarf star to have lived and died naturally. The universe is, in this sense, still young, and its most common stars are only just settling in for the long duration of their unhurried lives. In approximately 5 billion years, when the Sun exhausts the hydrogen in its core, it will begin a transformation that will remake the entire inner solar system. As fusion moves outward into a shell around the cooling core, the Sun's outer layers will expand enormously, swelling into a red giant perhaps 100 to 200 times its current size. Mercury will almost certainly be engulfed and vaporized. Venus, too, will likely be swallowed. Whether Earth survives depends on a fascinating cosmic race. As the Sun loses mass during its giant phase, Earth's orbit will expand outward in response, potentially moving far enough to escape the swelling star. But if the expansion happens faster than the orbit can shift, Earth too may be consumed. Scientists continue to debate which outcome is more likely. There is a quiet poetry in not knowing, in the fact that the fate of our world, 5 billion years from now, hinges on a subtle balance between two astronomical processes, each playing out on timescales that dwarf the entire history of life on Earth. After a Sun-like star exhausts its nuclear fuel and passes through its red giant phase, its outer layers drift away into space as a glowing planetary nebula, one of the most visually beautiful structures in the cosmos. What remains at the center is a white dwarf, the exposed core of the former star, roughly the size of Earth but containing the mass of the Sun, slowly cooling over billions of years. A white dwarf no longer generates energy through fusion. It is simply radiating the heat it still holds from its former life, like an ember that no longer burns but still glows. Over billions and trillions of years, longer than the current age of the universe, a white dwarf would cool until it became a black dwarf, a cold, dark, inert sphere floating silently in space. But the universe has not yet been in existence long enough for a single black dwarf to have formed. Every white dwarf in the sky today is still warm, still glowing, still releasing the stored warmth of a life spent burning. They are the quiet, patient, lasting embers of stars that once lit the sky. There is a persistent and understandable misconception that black holes roam through space like cosmic vacuum cleaners, pulling in everything in their vicinity with irresistible hunger. In reality, a black hole does not exert any greater gravitational pull at a distance than any other object of the same mass would. If our Sun were somehow replaced by a black hole of identical mass, which would require compressing all of the Sun's material into a sphere only a few miles across, the planets of our solar system would continue to orbit on exactly the same paths they follow today. Nothing would be pulled inward. The black hole's gravity at the distance of Earth would be identical to the Sun's gravity. What makes a black hole extreme is what happens very close to it. Only objects that venture within the event horizon, that critical boundary from which escape is impossible, are irretrievably captured. At a safe distance, a black hole is simply another massive object, warping space-time according to the same laws that govern everything else. At the center of our Milky Way galaxy, 26,000 light-years from Earth, there is a supermassive black hole known as Sagittarius, a star, and it is 4 million times the mass of the Sun. We cannot see it directly. It lies behind vast clouds of gas and dust, and black holes by their nature emit no light. But astronomers have tracked the orbits of stars very close to the galactic center and found that they move in precisely the ways predicted for objects orbiting an enormous, invisible, compact mass. One star, designated S2, orbits Sagittarius A star with a closest approach of only about 120 astronomical units, roughly 3 times the distance from the Sun to Pluto, and completes one orbit every 16 years. By watching S2 and its neighbors move, astronomers have mapped the gravitational influence of Sagittarius A star with remarkable precision. It sits at the heart of our galaxy, quiet and massive and dark, the gravitational anchor around which hundreds of billions of stars, including our own Sun, trace their slow and patient orbits. In April 2019, the world saw for the first time in history an actual image of a black hole. Not an artist's illustration, not a computer simulation, but a real photograph assembled from radio telescope data collected across the entire planet. The target was the supermassive black hole at the center of galaxy M87, located 55 million light-years from Earth and containing mass equivalent to 6.5 billion suns. The image, a luminous orange and red ring of glowing gas surrounding a dark central shadow, was assembled by the Event Horizon Telescope, a collaboration of radio observatories spanning from Hawaii to the South Pole, functioning together as a single Earth-sized instrument. The dark region at the center is the black hole's shadow, the event horizon and the region around it, where light has been captured and cannot escape. This image, blurry and distant and hard-won by years of planning and calculation, is one of the most extraordinary photographs ever taken. A direct look at an object whose existence was once considered theoretical, confirming a prediction made more than a century ago. If you could watch a person falling toward a black hole from a safe distance, you would never see them actually cross the event horizon. As they fell deeper into the black hole's gravitational field, time dilation would slow their apparent movement from your perspective. They would appear to slow down as they approached the event horizon, their movements growing increasingly sluggish, their image growing dimmer and redder as the light they emitted was increasingly stretched by gravity. Eventually, they would appear to freeze, a fading, reddening image hanging forever at the boundary, growing dimmer with each passing century until they simply faded into invisibility. To the person falling, however, nothing dramatic would happen at the moment of crossing. They would pass through the event horizon without any special sensation, the boundary invisible and physically unmarked. They would simply be inside, where the future no longer includes escape, and the singularity waits somewhere ahead. The same event, experienced from 2 different places in space-time, produces 2 entirely different stories. In 1974, the physicist Stephen Hawking predicted something that seemed almost paradoxical. Black holes, the most absolute traps in the universe, slowly lose energy and mass over time, and will eventually, after an almost incomprehensible span of time, evaporate entirely. This process, now called Hawking radiation, arises from quantum mechanical effects near the event horizon. In the vacuum of space, quantum theory predicts that pairs of virtual particles, one with positive energy, one with negative energy, are constantly being created and immediately annihilating each other. Near a black hole's event horizon, one particle can fall inside while the other escapes into space. The escaping particle carries positive energy away from the black hole, which must therefore lose an equivalent amount of mass over time. The rate is extraordinarily slow. A stellar mass black hole would take far longer than the current age of the universe to evaporate, and Hawking radiation has never been directly observed. But it represents a profound linking of quantum mechanics and gravity, 2 great theories that otherwise have resisted unification. Not all black holes are the supermassive giants that anchor the centers of galaxies. The most common type, stellar black holes, formed in the core collapse of massive stars, are comparatively modest, typically ranging from about 5 to 100 times the mass of the Sun. They are still extraordinary objects, of course. Anything whose event horizon radius spans just a few miles yet contains the mass of many suns is extraordinary by any reasonable measure. But they do not anchor galaxies. They drift through space, sometimes in pairs, sometimes orbiting ordinary companion stars, sometimes entirely alone in the dark. When a stellar black hole has a companion star, it can slowly draw material from that companion into an accretion disk, a swirling ring of heated gas that glows intensely in X-rays before crossing the event horizon. These X-ray binary systems are among the brightest X-ray sources in the sky, and they are how astronomers most easily identify stellar black holes, not by seeing the black hole itself, but by watching the brilliant spiral of matter being drawn toward it. If you were unfortunate enough to fall into a small black hole, one of stellar mass, a few times the mass of the Sun, the tidal forces would become lethal long before you crossed the event horizon. Tidal forces arise from the difference in gravitational pull between your head and your feet. The part of your body closer to the black hole experiences significantly stronger gravity than the part farther away, and this difference stretches you along the direction of the fall while compressing you from the sides. Near a small black hole, this difference would be enormous, strong enough to stretch a human body into a thin, elongated strand of matter, drawn out like taffy, a process physicists have with characteristic wit named spaghettification. For a supermassive black hole, one of billions of solar masses, the tidal forces at the event horizon are actually gentle enough that you might cross without discomfort, because the curvature is spread across such an enormous volume of space. The singularity would still await you, but the crossing would be smooth. It is one of the stranger truths of black hole physics. Bigger is in some ways gentler. Black holes can seem like rare and exotic exceptions to the normal rules of the universe, frightening anomalies in the otherwise orderly structure of space, but they are, by any reasonable measure, quite common. Astronomers estimate that the Milky Way galaxy alone contains somewhere between 10 million and 1 billion stellar mass black holes, formed over the galaxy's long history as massive stars have lived and died. This means that even in our own galaxy, black holes are scattered throughout, embedded in the stellar fabric like seeds, most of them dark and isolated and impossible to detect from a distance. The nearest known black hole to Earth, a system called Gaia BH1, discovered in 2022, is approximately 1,560 light-years away. That sounds distant, and by human standards it is immeasurably so, but on a galactic scale it is our cosmic neighbor. Black holes are not distant anomalies at the edges of the universe. They are woven into the ordinary structure of the galaxy we call home. The observable universe, the portion of the universe from which light has had time to reach us since the Big Bang, is approximately 93 billion light-years in diameter. This number surprises many people because the universe is only 13.8 billion years old and light travels at a finite speed. How can we see 46 billion light-years in any direction if the universe has only existed for 13.8 billion years? The answer is that space itself has been expanding during all that time. Light that left a distant region 13.8 billion years ago has been traveling toward us, but the space it was traveling through has been stretching, carrying the source of that light far beyond where it started. The universe we can observe is not the entirety of what exists. It is simply the portion from which light has had time to reach us, bounded not by a wall or an edge, but by the finite speed of light in an expanding space. Beyond the observable universe, the cosmos almost certainly continues, possibly forever, in directions we can never see and distances we can never cross. For much of the 20th century, astronomers estimated the observable universe contained somewhere around 200 billion galaxies. Then, in 2016, a more comprehensive analysis of Hubble Space Telescope data led researchers to revise that estimate dramatically upward, to at least 2 trillion galaxies, 10 times more than previously thought. Most of these galaxies are too small and too distant to be detected with current telescopes. They were inferred from statistical models and the distribution of light across the sky. 2 trillion is a number that the human mind was not built to comprehend. If you spent 1 second thinking about each galaxy, it would take 63,000 times the current age of the universe to think about them all. Each of those galaxies contains on average hundreds of billions of stars. The total number of stars in the observable universe is estimated at around 200 sextillion, a 2 followed by 23 zeros. Somewhere in that incomprehensible arithmetic, an ordinary yellow star called the Sun quietly burns, and around it a small blue-green world turns. And on that world you are lying here, breathing, drifting towards sleep. The human mind naturally reaches for analogies when confronting the scale of the universe, and one of the most illuminating is this. If our Sun were shrunk to the size of a single grain of sand, the Milky Way galaxy, all 100,000 light-years of it, would still be roughly the size of a continent. A grain of sand is about 1 millimeter across. A continent is thousands of kilometers wide. The ratio between them is approximately the same as the ratio between the diameter of the Sun and the diameter of the Milky Way. And the Milky Way is not a large galaxy by cosmic standards. There are galaxies hundreds of times more massive. The scale of the universe does not compress into intuition, no matter how carefully one tries. It simply exists beyond the human scale, a reality so much larger than ordinary experience that it can only be held mathematically in equations and ratios and enormous numbers. What the mind cannot hold in full, it can still approach with wonder, which may, in the end, be the more honest response to a universe this large. If you could step outside the universe and look at it from an enormous distance, you would see something resembling a vast three-dimensional web. Galaxies do not distribute themselves randomly through space. They cluster together, drawn by mutual gravity into groups and clusters and superclusters, which in turn are arranged along enormous filaments of matter, threads and sheets of galaxies stretching hundreds of millions of light-years. Between these filaments lie vast cosmic voids, regions almost entirely empty of galaxies, spanning hundreds of millions of light-years in every direction. This large-scale structure, the cosmic web, emerged from tiny fluctuations in the early universe, infinitesimally small variations in density that gravity then amplified over billions of years into the architecture we see today. Computer simulations of the universe's evolution, running forward from the Big Bang with only a few basic physical laws, reproduce this cosmic web with striking accuracy. The universe, it turns out, has a structure, a vast and beautiful geometry that grew from almost nothing, patiently, over 13.8 billion years. The universe is not expanding into anything. This is one of the hardest ideas in cosmology to hold comfortably, because our intuition insists that expansion must mean expansion into something, that there must be empty space beyond the boundary of the universe into which it is growing. But there is no beyond. The expansion of the universe is not the movement of galaxies outward through pre-existing space. It is the stretching of space itself. The fabric of space-time growing larger, carrying the galaxies within it apart from one another, the way dots drawn on the surface of a balloon move apart when the balloon is inflated. The balloon analogy is imperfect, as all analogies are, but it captures the essential strangeness. The surface of the balloon is not expanding into the space inside or outside the balloon. The surface itself is growing. In the same way, there is no edge to the universe, no exterior, no boundary. Space is simply more of itself in every direction, and it is quietly becoming even more so all the time. The most distant object ever observed by astronomers is a galaxy that existed when the universe was only approximately 320 million years old, less than 2.5% of its current age. This galaxy, detected by the James Webb Space Telescope and designated JADIS GSZ 14-0, has been observed as it was nearly 13.5 billion years ago, making its light among the oldest ever captured by human instruments. Looking at it, we are looking at the early universe in the way you might look at a photograph of someone as an infant. The subject has changed almost entirely since the image was made, and what we see is a record of a moment long past. The galaxy itself, as it exists today, has had 13.5 billion years to evolve, to merge with other galaxies, to form new stars, to age and change in ways we cannot know without newer light, which will take another 13.5 billion years to arrive. We are always looking at history in astronomy. The present is the one thing the universe, across all its distances, cannot show us. Between the galaxies in the cosmic web lie the voids, regions of space so empty and so cold that they represent the closest thing to nothing that the universe actually contains. These voids can span hundreds of millions of light-years in every direction, containing only a handful of isolated galaxies where a region that size might typically hold thousands. The temperature inside a cosmic void is just barely above absolute zero, a few degrees above the background temperature of the universe, and the density of matter is extraordinarily low. There are no stars here, no planets, no warmth, no light save for the faint cosmic background. Just space itself, stretching in every direction, almost but not quite empty, threaded with dark matter, permeated with the faintest glow of ancient light. These voids are among the largest and most serene structures in the universe, vast quiet regions where nothing much has been happening for billions of years and almost nothing is happening now. They are, in their immense and empty way, the universe's most peaceful places. Our galaxy, the Milky Way, is a barred spiral galaxy approximately 100,000 light-years in diameter, containing an estimated 100 to 400 billion stars, along with vast clouds of gas and dust, numerous star clusters, and a supermassive black hole at its center. Its thin disk of stars is arranged in a series of spiral arms wrapping outward from the central bar, and the entire structure rotates slowly, with our solar system completing one full orbit around the galactic center approximately every 225 to 250 million years, a period sometimes called a cosmic year or galactic year. The last time we were at our current position in the galaxy, the dinosaurs had not yet existed. In the cosmic year before that, the most complex life on Earth was marine invertebrates. The Milky Way has completed roughly 60 such rotations since it formed, and our Sun has completed about 20 of its own galactic orbits since it came into existence. We are, by any measure, long-time residents of a very old and very large neighborhood. Our solar system sits approximately 26,000 light-years from the galactic center, roughly halfway between the center and the outer edge of the Milky Way's disk, located in a relatively quiet region called the Orion Arm, a minor spiral feature between the larger Perseus and Sagittarius arms. This location turns out to be rather pleasant from a cosmic habitability standpoint. The galactic center is a far more violent environment, dense with stars, intense radiation, and the gravitational influence of Sagittarius A star. The outer edges of the galaxy have fewer of the heavy elements needed to form rocky planets and complex chemistry, because heavy elements are forged in massive stars and accumulate over time near regions of ongoing star formation. Our position in the middle regions of the Milky Way offers a balance, enough heavy elements from billions of years of stellar evolution, but not so much radiation and gravitational turbulence that complex life would struggle to take hold. We are located, in some sense, in the galaxy's habitable zone, a quiet neighborhood in a vast and varied city. The Andromeda Galaxy, our nearest large galactic neighbor, 2.537 million light-years away and containing roughly 1 trillion stars, is not staying where it is. It is approaching the Milky Way at approximately 110 kilometers per second, drawn by the mutual gravitational attraction between the two galaxies, and in approximately 4.5 billion years, the two galaxies will collide and begin a slow, complex process of merging that will unfold over billions more years. The word collision is somewhat misleading. Galaxies are mostly empty space, and the individual stars within them are so widely separated that the chance of any two stars actually striking each other is negligibly small. What will happen is that the two galaxies' shapes will be disrupted, their spiral structures distorted and torn, their stars redistributed into new orbits around a combined center, ultimately forming a new, larger elliptical galaxy. Our Sun and solar system will survive this process, though they will likely end up in a very different location within the merged galaxy. The night sky, 4 billion years from now, will be spectacular. Everything you have ever seen, touched, or interacted with, every atom of every object on Earth, every star in every galaxy, every planet and moon and comet and cloud of gas in the observable universe, makes up only about 5% of the total content of the universe. 5%. The matter we can detect, measure, catalogue, and understand constitutes a small fraction of what is actually there, with the remaining 95% consisting of two components we have named but cannot yet directly detect, examine, or fully explain. This is not a provisional estimate waiting to be corrected. It is a well-established conclusion drawn from multiple independent lines of evidence, including the rotation of galaxies, the large-scale structure of the universe, the cosmic microwave background, and the behavior of galaxy clusters. We live in a universe that is, in a very real sense, mostly unknown. The stars and galaxies that fill our sky and inspire our imaginations are the luminous froth on the surface of something much larger and far less understood. Dark matter is the name given to whatever accounts for the additional gravitational effects observed in galaxies and galaxy clusters, effects that cannot be explained by the visible matter alone. When astronomers measure the rotational speeds of galaxies, they find that the outer parts of the galaxy rotate just as fast as the inner parts, which should not be the case if the only mass present is the visible stars and gas. To maintain those outer rotation speeds, there must be significantly more mass than what we can see, distributed not just in the visible disk of the galaxy, but in a large, roughly spherical halo extending far beyond the visible structure. This additional mass is dark matter. It does not emit light. It does not reflect light. It does not absorb light. It interacts with ordinary matter only through gravity. No one knows what it is made of. Dozens of particle candidates have been proposed, and decades of experiments have been designed to detect it directly, but as of today, it has resisted all attempts at direct identification. It is there, its gravitational fingerprint is unmistakable, but its nature remains one of the most important open questions in all of science. Dark energy is the name given to whatever is driving the accelerating expansion of the universe, a force or property of space itself that is causing the galaxies to fly apart from one another at an ever-increasing rate. It makes up approximately 68% of the total content of the universe, making it the single dominant component, and yet it is the least understood of all. One candidate is something Einstein called the cosmological constant, a term he added to and then removed from his equations, which represents an intrinsic energy density of empty space, a property of the vacuum itself that provides a gentle, repulsive pressure pushing space-time outward. Whether dark energy is the cosmological constant, or something that changes over time, or something entirely outside current theoretical frameworks, is unknown. What is known is that it exists, that it is winning its expansion battle against gravity on the largest scales, and that its influence will grow with time as the universe stretches and the galaxies drift ever farther apart into an increasingly empty and dark cosmic future. Dark matter and dark energy are among the most consequential unsolved mysteries in all of physics and cosmology. Together they make up 95% of the universe's content, and together they are completely unknown at the level of fundamental physical explanation. We know dark matter exists because of what it does, the gravity it exerts, the structure it creates, the way it organizes galaxies. We know dark energy exists because of what it causes, the accelerating expansion, the retreating of galaxies, the stretching of space-time. But knowing what something does is very different from knowing what it is. What particles, if any, make up dark matter? Is dark energy constant or does it vary? Are they related to each other? Is dark energy truly a property of empty space, or is it a new kind of field? These questions are not minor details to be worked out in due time. They are the central questions of modern cosmology, and their answers, when they come, may reshape our understanding of physics as profoundly as relativity and quantum mechanics did in the 20th century. The first strong evidence for dark matter emerged from the study of galaxy rotation curves, measurements of how quickly different parts of a galaxy orbit the galactic center. According to the laws of gravity, the parts of a galaxy farthest from the center should orbit more slowly, just as the outer planets of our solar system orbit the Sun more slowly than the inner ones. But when astronomers measured the rotation curves of spiral galaxies in the 1970s, particularly through the pioneering work of Vera Rubin and her colleagues, they found something unexpected. The rotation curves were flat. The outer regions of galaxies were orbiting just as fast as the inner regions, sometimes even faster. The only explanation consistent with the laws of gravity was that there was significantly more mass in and around these galaxies than what was visible. invisible mass distributed throughout a large halo surrounding the visible disk. This was not a small correction. To match the observed rotation curves, galaxies had to contain roughly 5 to 6 times as much dark matter as visible matter. The discovery quietly transformed our picture of what galaxies actually are. One of the stranger properties of dark matter, whatever it is that it appears to interact with ordinary matter only through gravity, passing through normal atoms and molecules as if they were not there. When two galaxy clusters collide, the visible gas clouds within them slow down and interact, heating up and emitting X-rays, while the dark matter halos simply pass through each other, barely interacting at all. This has been directly observed in the Bullet cluster. Two galaxy clusters in the aftermath of a collision, where gravitational lensing reveals the dark matter distribution extending far beyond and separate from the heated gas. If dark matter passed through ordinary matter in this way during the formation of our solar system, it passed through the forming Earth, through the ancient oceans, through the first living cells, through every creature that has ever lived, through every human building and every human body, on its way to wherever it was going. It may be passing through you right now, at this very moment, as quietly and completely as if you did not exist. In 1998, two independent research teams studying distant supernovae made a discovery that surprised almost everyone in cosmology and earned its leaders the Nobel Prize in Physics 13 years later. They were measuring the distances to Type 1a supernovae, a type of stellar explosion of known intrinsic brightness, usable as a standard candle for measuring cosmic distances. What they expected to find was that the expansion of the universe, ongoing since the Big Bang, was slowly decelerating, slowing down under the mutual gravitational attraction of all the matter in the universe. What they found instead was the opposite. The universe's expansion was accelerating. The most distant supernova were farther away than they should have been if gravity had been the only influence, meaning that space had been stretching faster and faster, not slower and slower. Something was pushing the universe outward. That something was named dark energy, and its discovery fundamentally changed our picture of the universe's past, present, and future. If dark energy continues to strengthen over cosmic time, as some theoretical models suggest is possible, the ultimate fate of the universe could be something physicists call the Big Rip. In this scenario, the energy of expansion would grow so powerful that it would eventually overcome not just the gravity-holding galaxy clusters together, but the gravity-holding individual galaxies together, then the gravity-holding solar systems together, then the molecular bonds holding planets and rocks, and eventually atoms themselves together. The universe would be torn apart at every scale, from the largest structures to the smallest, in a cascade of dissolution culminating in the ripping apart of atomic nuclei. This would not happen for a very long time. Estimates place it, if it occurs at all, tens of billions of years in the future. And it is only one possible end state, dependent on the precise nature of dark energy, which remains unknown. The future is not decided. The universe is still writing that part of its story, and the ending has not yet been settled. Jupiter's Great Red Spot is a storm, an enormous, ancient, high-pressure atmospheric system that has been swirling in Jupiter's clouds for at least 350 years, and possibly much longer. At its largest historical measurements, the storm was wide enough to contain 2 or 3 Earths side by side. It rotates counterclockwise, completing a full rotation roughly every 6 days, and it persists because Jupiter's atmosphere has no solid surface to disrupt it the way that land masses on Earth eventually break up large weather systems. In recent decades, the Great Red Spot has been observed to be shrinking. It is significantly smaller now than it was a century ago, and whether it will persist indefinitely, slowly dwindle, or eventually dissipate is a subject of ongoing observation. What has endured for centuries in Jupiter's stormy, banded atmosphere is already extraordinary by the standards of any weather system in our experience. The largest hurricane in Earth's recorded history lasted a matter of weeks. Jupiter's oldest storm has been raging since before the invention of the steam engine. Saturn's rings are one of the most visually stunning structures in the solar system. Vast, flat, luminous halos of ice and rock that encircle the planet in a disk extending up to 282,000 kilometers from Saturn's center, yet in most places only 10 to 30 meters thick. The rings are composed mostly of water ice, ranging in particle size from tiny grains smaller than a grain of sand to chunks as large as a house, and they reflect sunlight with brilliant efficiency, making Saturn and its rings among the brightest objects visible through a small telescope. The rings are not permanent fixtures of the solar system. They are estimated to be relatively young, perhaps only 100 to 400 million years old, possibly formed from the debris of a moon torn apart by tidal forces or shattered by an impact, and they are slowly being lost as ring material spirals inward towards Saturn's atmosphere in a process called ring rain. In another 100 million years or so, they may be gone entirely, a feature of Saturn that exists in this particular window of solar system history, visible from Earth precisely because we happen to be here to see them. Venus is a planet of remarkable extremes, and among its stranger properties is this: a day on Venus, the time it takes to complete one full rotation on its own axis, is longer than a year on Venus, the time it takes to complete one full orbit around the Sun. Venus rotates so slowly, with a sidereal rotation period of approximately 243 Earth days, that it completes its orbit around the Sun in 225 Earth days before it finishes even one full rotation. And as if that were not peculiar enough, Venus rotates in the opposite direction from most planets in the solar system, clockwise when viewed from above the solar system's north pole, whereas Earth and most other planets rotate counterclockwise. This retrograde rotation means that on Venus, if you could stand on the surface and see through the thick cloud cover, the Sun would rise in the west and set in the east. The reasons for this unusual rotation are still debated, but may involve a past collision or the gravitational and atmospheric torques of the Sun acting on Venus over billions of years. Mars is home to the largest volcano in the solar system, a shield volcano called Olympus Mons that stands approximately 22 kilometers high, nearly 3 times the height of Mount Everest, and spans approximately 600 kilometers across, roughly the size of the state of Arizona. To stand at the base of Olympus Mons and look toward its summit would be impossible in the ordinary sense. The volcano is so wide that its edges curve below the horizon before the summit comes into view. Its slopes are gentle by mountain standards, rising at an average grade of only a few degrees, which is why it could grow so tall without collapsing under its own weight. Olympus Mons grew to such extraordinary size because Mars, unlike Earth, does not have tectonic plates that move the crust laterally over volcanic hotspots. On Earth, the movement of tectonic plates carries the crust over a stationary hotspot, producing a chain of volcanoes, like the Hawaiian Islands. On Mars, the crust stayed still and the volcano simply kept growing upward, eruption after eruption, for hundreds of millions of years. One of the most scientifically exciting objects in the solar system is Europa, a moon of Jupiter roughly the size of Earth's own moon, covered in a smooth shell of water ice and believed to harbor a vast liquid water ocean beneath it. The evidence for this subsurface ocean is compelling. The icy surface shows signs of geological activity inconsistent with a solid interior, including fracture patterns and surface features that suggest movement of liquid water below. The tidal heating caused by Jupiter's powerful gravity flexing Europa's interior provides the energy to keep this ocean liquid despite the moon's extreme distance from the Sun. This combination, liquid water, chemical energy from the interaction of the ocean with a rocky seafloor, and organic molecules carried in by cometary impacts, represents the conditions that, on Earth, gave rise to life. Whether life exists in Europa's dark, pressurized ocean is one of the most profound open questions in planetary science. A spacecraft called Europa Clipper is on its way to study this remarkable moon in detail, carrying the hopes of anyone who has ever wondered whether life exists beyond Earth. Saturn is the only planet in our solar system with an average density lower than that of water. If you could somehow construct an ocean large enough to hold it, a vessel of water roughly large enough to contain a planet, Saturn would float. Its average density is approximately 0.687 grams per cubic centimeter, compared to water's 1.0 grams per cubic centimeter, making it less dense than the liquid that covers most of Earth's surface. This is not because Saturn is hollow or made of light material. It is composed primarily of hydrogen and helium, the lightest elements in the universe, and its enormous size means that much of its volume is occupied by low-density gas rather than dense rock or metal. Deep inside, the pressure is high enough to compress hydrogen into a liquid and then into a metallic state. But on average, across the whole enormous sphere, the density is lower than water. This fact, small and curious as it sounds, reveals something important about the nature of the gas giants. They are not scaled-up versions of rocky worlds. They are fundamentally different kinds of things, made of the same raw materials as stars, just not quite massive enough to burn. While most planets in the solar system rotate with their axes roughly perpendicular to the plane of their orbits, tilted anywhere from a few degrees to about 28 degrees, as in Earth's case, Uranus is tilted at approximately 98 degrees, which means it essentially rotates on its side. Its north pole points almost directly toward the Sun for half of its 84-year orbit, and its south pole points almost directly toward the Sun for the other half. This gives Uranus the most extreme seasons of any planet in the solar system, with each pole experiencing approximately 42 years of continuous sunlight, followed by 42 years of continuous darkness. The most widely accepted explanation for this extraordinary tilt is that early in the solar system's history, Uranus suffered a catastrophic impact with an Earth-sized or larger object, which knocked it onto its side. The evidence for this is largely circumstantial. The right culprit has never been definitively identified, but no other natural mechanism has been found that adequately explains why one planet in a solar system of mostly upright worlds would be lying at such an improbable angle. Neptune is the windiest planet in the solar system, a cold and distant blue world where winds in its upper atmosphere can reach speeds of over 1,200 miles per hour, faster than the speed of sound on Earth, and faster than any other winds measured on any other planet. This is deeply counterintuitive because Neptune receives only about 0.1% as much sunlight as Earth, and sunlight is the primary driver of atmospheric dynamics on planets like Earth. Neptune's powerful winds are not well understood, and explanations range from heat escaping from the planet's interior — Neptune emits more heat than it receives from the Sun — to some property of low-viscosity cold hydrogen that allows it to channel energy into wind more efficiently than warmer atmospheres. The winds form dark storm systems that can grow to the size of Earth and persist for years before dissipating. Neptune is a world of quiet extremes, distant, cold, dark and nearly invisible from Earth, yet inside its atmosphere a fury that makes any storm in human experience look gentle. Pluto, the most famous of the dwarf planets, shares its space with a companion moon called Charon that is so large in comparison, more than half the diameter of Pluto, that the two bodies do not orbit each other in the usual sense of one body circling the other. Instead, both Pluto and Charon orbit a common center of mass called a barycenter, which lies in the space between them rather than inside either body. This makes Pluto and Charon, in a sense, a double dwarf planet system, two worlds locked in a slow, mutual dance, each keeping the same face permanently turned toward the other, both tidally locked in a gravitational embrace. The New Horizons spacecraft, which flew past Pluto in 2015 and sent back the first close images of this distant world, revealed a heart-shaped nitrogen ice plain on Pluto's surface and a rugged, cratered terrain on Charon. These small, cold worlds at the edge of the solar system turned out to be geologically interesting and visually beautiful, a reminder that even the most distant and unassuming corners of our neighborhood are worth a closer look. The sun does not simply shine, it exhales. A constant stream of charged particles, mostly electrons and protons, flows outward from the sun in all directions at speeds of 250 to 750 kilometers per second. This is the solar wind, and it fills the entire solar system, shaping the environment of every planet and moon it touches. When the solar wind reaches Earth, it is deflected by our planet's magnetic field, which acts as an invisible shield, bending the stream of particles around us and protecting the surface from their potentially damaging effects. Where the solar wind and the magnetic field interact at high latitudes, some particles funnel down along magnetic field lines into Earth's upper atmosphere and collide with gas molecules, causing them to glow in curtains and sheets of shifting light. The aurora borealis in the north, the aurora australis in the south. These luminous displays, gentle and beautiful, are the visible evidence of the solar wind encountering Earth's protective field, a reminder that we live inside the atmosphere of our star and that its breath reaches us every day, answered by the quiet glow of the northern lights. The second law of thermodynamics is one of the most fundamental and, to many physicists, most profound laws in science. It states that in any closed system, the total entropy, a measure of disorder or the number of possible configurations the system can be in, will always increase over time, or at best remain constant. It will never decrease. Entropy is why heat flows from hot objects to cold ones and never spontaneously in the other direction. It is why a drop of ink disperses through water and never spontaneously reassembles. It is why eggs break but do not unbreak, why perfume spreads through a room but does not gather back into the bottle, why everything complex and ordered tends, given enough time and without input of energy, to dissolve into simpler, more disordered states. This law is not merely a tendency or a statistical likelihood. It is a constraint on the direction of time, a one-way gate built into the very structure of physical reality. The universe is, on the whole and in the very long run, inexorably moving toward a state of greater disorder, and it has been doing so since the moment it began. The universe at the moment of the Big Bang was in an extraordinarily low entropy, highly ordered state, a condition of remarkable uniformity and almost incomprehensible density, where matter and energy were so smoothly distributed that the tiniest fluctuations from perfect uniformity were the seeds of all the structure that would eventually grow. From that highly ordered initial state, the universe has been evolving toward greater entropy ever since, and the direction of that evolution, toward greater disorder, greater distribution of energy, more evenly spread matter, defines what we call the arrow of time. The fact that the universe began in such a remarkably low entropy state is itself a deep puzzle. Why would the universe start in such an ordered condition? There is no universally agreed upon answer. Some physicists think it is a feature of whatever mechanism created the universe. Others think it is a selection effect. Only universes that begin in low entropy states allow complexity and life to emerge, so by definition, any universe with observers in it began this way. The question touches on the origins of time itself. In a universe steadily moving toward greater disorder, stars represent extraordinary local exceptions, temporary pockets of organization and energy, drawing together diffuse gas into dense, luminous, structured objects that pour energy into their surroundings for billions of years. They do not violate the second law of thermodynamics. The creation and maintenance of a star increases the total entropy of the universe because the energy released by fusion is spread outward as radiation, increasing the disorder of the surrounding space. But locally, within the star and its sphere of influence, extraordinary order is maintained. Nuclear fusion producing specific elements, gravity organizing the star into a coherent structure, energy flowing outward in a steady and predictable stream. Life itself is another such pocket, a local, temporary organization maintained by consuming and transforming energy, always increasing entropy overall while sustaining improbable complexity locally. Every living thing on Earth, every star in the sky, every organized structure in the universe is a brief and beautiful eddy in the long river of entropy, swimming against the current for as long as its energy holds out. The coldest known place in the observable universe is not in the depths of intergalactic space, but inside a planetary nebula called the Boomerang Nebula, located approximately 5,000 light-years from Earth in the constellation Centaurus. At its core, the Boomerang Nebula has a temperature of approximately -458 degrees Fahrenheit, just 1 degree above absolute zero, and colder even than the ambient temperature of the cosmic microwave background radiation that permeates all of space. This extraordinary cold arises from the rapid expansion of gas being ejected from a dying star at its center, moving outward at about 164 kilometers per second. As the gas expands rapidly into the surrounding space, it cools through the same principle that makes an aerosol can feel cold when you spray it. The adiabatic expansion of a gas causes its temperature to drop. The star at the center is in the late stages of its life, shedding its outer layers into space in a process that, over thousands of years, will form a glowing planetary nebula. Right now, in this brief cold moment, it has created the universe's most frigid region. Absolute zero, the lowest theoretically possible temperature, is -459.67 degrees Fahrenheit, or 0 Kelvin, the base of the Kelvin temperature scale. At absolute zero, a substance would have the minimum possible thermal energy with its atoms in their lowest possible quantum mechanical state. The thermal vibrations of atoms, which constitute heat, would effectively cease. In practice, absolute zero can never be fully reached. The third law of thermodynamics states that as a system approaches absolute zero, the amount of work needed to cool it further approaches infinity. There is always some irreducible minimum of thermal activity that cannot be removed. Scientists have gotten extraordinarily close, reaching temperatures within a billionth of a degree of absolute zero in laboratory experiments, but the final fraction will always remain just out of reach. Absolute zero is less a physical place that matter can occupy than a theoretical limit that matter can approach asymptotically, always getting closer, never quite arriving. It is the universe's most elusive destination, a temperature at which nothing can quite come to rest. If the universe continues its current trajectory, expanding, cooling, with entropy continuously increasing, it will eventually reach a state known as the heat death of the universe. This is not death in the dramatic sense of explosion or collapse, but rather its opposite. A slow, vast, patient dissolution into maximum entropy. A state where energy is distributed so evenly throughout space that no temperature differences exist anywhere and no work can be done. Stars will have all burned out. Black holes will have evaporated via Hawking radiation over timescales so enormous they make the current age of the universe seem like an instant. The last structures to persist will be the final evaporating black holes, each one shrinking over trillions upon trillions of years until, in a final faint burst of Hawking radiation, they too are gone. What remains is an utterly dark, cold, evenly distributed collection of the most stable elementary particles, a universe at maximum entropy, where nothing can change and nothing will ever happen again. This fate is incomprehensibly distant, but the universe is already, patiently and without hurry, working its way toward it. Space, far from any star or galaxy, is not truly empty, and it is not truly at absolute zero. The entire universe is permeated by the cosmic microwave background radiation, the relic glow of the early universe, and this radiation gives all of space a background temperature of approximately 2.73 Kelvin, or about -454 degrees Fahrenheit. This is extraordinarily cold by any human standard, but it is measurable, real warmth, and it means that nothing in the universe is completely without thermal energy. An object placed in deep intergalactic space would not simply cool to absolute zero. It would settle at approximately this background temperature, warmed by the faint ancient glow of the cosmos itself. As the universe continues to expand, this background temperature will continue to fall very slowly as the radiation stretches to lower and lower energies. Far in the future, after the stars have all gone dark and the galaxies have dissolved, the universe's background temperature will approach but never quite reach absolute zero, cooling toward the silence of heat death, one infinitesimal fraction of a degree at a time. Einstein's special theory of relativity, published in 1905, contains a prediction that still feels strange no matter how many times one encounters it. Moving clocks run slow, not because of any mechanical flaw or friction or imperfection in the clock, but because time itself passes more slowly for objects in motion relative to a stationary observer. This is time dilation, and it has been confirmed by experiment many times over. Atomic clocks flown around the world on aircraft tick slightly slower than identical clocks left on the ground. Muons, unstable subatomic particles created in the upper atmosphere by cosmic rays, survive long enough to reach Earth's surface because, traveling at nearly the speed of light, time passes slowly for them and they decay more slowly than they would at rest. The effect is too small to notice in everyday life, where nothing moves fast enough for the dilation to be perceptible. But it is real, measurable, and consistent with every test it has been subjected to. Time is not a fixed background against which events play out. It is a flexible dimension, shaped by motion and gravity, that each object experiences in its own private way. One of the most famous thought experiments in physics is the twin paradox, which illustrates time dilation in a vivid and human way. Imagine a pair of twins, one of whom boards a spacecraft and travels at a significant fraction of the speed of light toward a distant star, while the other remains on Earth. From the traveling twin's perspective, time passes normally. A year feels like a year, the heart beats once a second, sleep comes every night. But the journey that feels like a year or two to the traveler might correspond to decades passing on Earth. When the traveling twin returns, they are younger than their sibling who stayed behind. This is not a paradox in the sense of a contradiction. It is a genuine, verified physical reality. Astronauts who have spent extended time on the International Space Station are, when they return to Earth, very slightly younger than they would have been had they stayed on the ground, by fractions of a second due to both velocity and the slightly weaker gravity at orbital altitude. Time for every traveler is personal. It belongs to the path you have taken, not to the world you left behind. As an object moves faster, accelerating it further requires more and more energy. Not because its intrinsic mass is changing, but because its relativistic momentum grows without bound as it approaches the speed of light. An object's rest mass, the mass it has when standing still, never changes. But the momentum of a moving object, in Einstein's framework, is not simply mass times velocity as Newton described it. It contains an additional factor that increases as velocity increases, growing toward infinity as the velocity approaches the speed of light. The result is that accelerating an object to higher and higher fractions of the speed of light requires progressively greater amounts of energy, in a way that diverges to infinity at the light barrier. No finite amount of energy can push anything with mass to the speed of light. This is why the speed of light is an absolute speed limit, not a technological barrier, not a limitation of current engineering, but a mathematical impossibility written into the structure of spacetime. The universe does not merely make it hard to reach the speed of light, it makes it impossible. The speed of light is not a record to be broken with better technology or greater effort. It is a hard limit inscribed in the mathematics of special relativity, and nothing with mass will ever reach it. Not because we have not tried hard enough, but because the energy required becomes infinite as the speed approaches that of light. To accelerate a proton to 99% of the speed of light requires a great deal of energy. To accelerate it to 99.9% requires much more. To accelerate it to 99.9999% requires enormously more still. The particle accelerators at CERN have pushed protons to within a fraction of a percent of the speed of light, and the energy required is in the billions of electron volts per proton. The final fraction of a percent toward the true speed of light would require infinite energy. This is not a problem of insufficient power. It is a feature of the geometry of space-time, which curves in such a way that the light barrier is genuinely unreachable. Light itself travels at this speed because photons have no rest mass. For everything else, the speed of light is the horizon at the end of every road, visible in every direction, never arrived at. In the quantum mechanical description of reality, a particle does not have a definite value for properties like position, momentum, or spin until it is measured. Before measurement, it exists in a superposition of multiple possible states simultaneously, not just unknown, but genuinely in multiple states at once, each with a certain probability. This is not a statement about our ignorance, it is a statement about physical reality. The electron in a hydrogen atom does not have a specific location. It exists in a spread-out cloud of probability that is its actual physical state, until an interaction collapses it to a specific position. Schrödinger's famous thought experiment about a cat in a box that is simultaneously alive and dead was intended as a reductio ad absurdum of this principle, a way of showing how strange it becomes when applied to large everyday objects. But at the quantum level, superposition is not strange at all. It is simply how reality operates. The weirdness only appears when we try to translate quantum behavior into the language of everyday experience, which is itself built from classical approximations that work well at our scale and fail completely at the atomic one. Werner Heisenberg's uncertainty principle, formulated in 1927, states that there is a fundamental limit to how precisely certain pairs of physical properties of a particle can be simultaneously known. The most famous pair is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast and in what direction it is moving, and vice versa. This is not a limitation of our instruments or our measurement techniques. It is a fundamental property of nature, a consequence of the fact that particles are described by quantum mechanical wave functions, and that determining one property precisely necessarily disturbs the other. The principle also applies to energy and time. A particle's energy cannot be precisely defined over an arbitrarily short time interval, which gives rise to the existence of virtual particles, brief quantum fluctuations of energy that can exist for a fleeting moment without violating energy conservation as long as they disappear quickly enough. The universe, at its most fundamental level, is not a collection of precisely defined objects following precisely defined paths. It is a probabilistic shimmer, definite only in what we choose to measure, indeterminate in everything else. Quantum entanglement is one of the most remarkable and genuinely strange phenomena in physics, a condition in which two particles become correlated in such a way that the quantum state of each cannot be described independently of the other, regardless of the distance between them. When two particles are entangled and you measure a property of one, its spin for instance, the other particle's corresponding property is immediately determined no matter how far apart they are. Einstein famously called this spooky action at a distance and believed it indicated something incomplete about quantum mechanics, since it seemed to imply an influence traveling faster than light. Subsequent experiments, particularly those testing what are known as Bell inequalities, have confirmed that the correlations are real and cannot be explained by any pre-existing agreement between the particles. The information does not travel faster than light. Entanglement cannot be used to send signals. But the correlations themselves are non-local, a genuine feature of the quantum fabric of reality that has no classical analog. Two particles, once entangled, are in some fundamental sense one system, regardless of the space between them. The Big Bang is often pictured as an explosion, a massive fireball erupting outward from a central point into pre-existing space. But this picture, while intuitive, is not accurate. The Big Bang was not an explosion in space. It was an explosion of space, the beginning of spacetime itself, in which the entire universe, in a state of unimaginable density and temperature, began expanding everywhere simultaneously. There was no center to the explosion and no exterior into which the universe expanded. Every point in the early universe was the origin point. Every location was expanding away from every other location. In the first fraction of a second, the universe underwent a period of exponential expansion called inflation, growing from a region smaller than a proton to macroscopic scales in an almost inconceivably brief moment. In the process, quantum fluctuations were stretched across cosmic distances, seeding the variations in density that would eventually grow into galaxies and cosmic structure. The universe did not begin somewhere and spread outward. It began everywhere at once, and every place in it carries the mark of that beginning. The flow of time, the fact that the past is fixed and the future is open, that we remember yesterday but not tomorrow, that events unfold in a direction from cause to effect, may not be a fundamental feature of physical reality, but rather an emergent property of the universe's thermodynamic history. The laws of physics at the fundamental level are almost entirely time-symmetric. The equations that describe the behavior of particles work equally well run forward or backward. There is no fundamental law that says time must flow in one direction rather than the other. The reason we experience time as having a direction, an arrow, is believed by many physicists to arise from the second law of thermodynamics and the fact that the universe began in an extraordinarily low entropy state. We remember the past because it is more ordered than the present. Events flow from lower entropy to higher entropy, not because time requires it, but because the universe's initial conditions made it statistically overwhelmingly likely. The arrow of time is, in this view, the shadow of the Big Bang, a direction imposed not by the laws of physics, but by the particular initial conditions of our universe. The fact that we remember the past and not the future, one of the most basic features of conscious experience, is, from a physics perspective, deeply connected to entropy and the initial conditions of the universe. Memory requires a physical record, a lower entropy encoding of a previous state, preserved in the structure of a brain or a book or a stone. Creating a memory of an event necessarily increases the total entropy of the universe slightly, and reading that memory means interacting with a lower entropy record of the past. The future cannot be remembered because its states have not yet been recorded. The low entropy encoding of a future event does not yet exist. This asymmetry, that the past is recorded and the future is not, traces back to the universe's low entropy beginning. Because the universe started in an ordered state and has been moving toward disorder, there is a consistent direction from which records can be made. The past, which was more ordered, leaves traces in the present. The present, in becoming the future's past, will leave traces for whatever observers come after. Memory, in this deep sense, is the universe's way of retaining information as it moves patiently and irreversibly in the direction of greater disorder. The aurora borealis, the northern lights, is one of the most beautiful natural phenomena visible from Earth, and it is the direct result of physics taking place at the boundary between our planet's magnetic field and the solar wind. When charged particles from the Sun, mostly electrons and protons, reach Earth, they are deflected by the magnetic field and guided toward the polar regions, where they spiral down along magnetic field lines into the upper atmosphere. There, they collide with oxygen and nitrogen molecules, transferring energy to the atom's electrons and exciting them to higher energy states. When those electrons fall back to their ground states, they release that energy as light, green from oxygen at lower altitudes, red from oxygen at higher altitudes, blue and purple from nitrogen. The result is the aurora, sweeping curtains of green and white and red and violet light, rippling and dancing across the polar sky in patterns that follow the invisible architecture of Earth's magnetic field. The lights you see are the sky's own luminous map of a field you cannot otherwise perceive, drawn in color by the breath of the sun. Every atom in your body heavier than hydrogen was forged inside a star. The oxygen filling your lungs right now was produced in the nuclear furnace of a massive star that lived and died billions of years before the sun was born. The carbon forming the backbone of every molecule of DNA in every cell of your body was assembled through triple alpha fusion in a stellar core. The iron that carries oxygen through your blood was produced in the final, most energetic phase of stellar fusion, just before a star too massive to survive collapsed and exploded, scattering its contents into space. The calcium in your bones, the nitrogen in your proteins, the phosphorus in your cell membranes, all of it came from stars. This is not a metaphor. It is biochemistry tracing itself back to astrophysics. The atoms that compose you traveled for billions of years through the interstellar medium before they were gathered into the cloud that became our solar system, woven into the Earth, cycled through oceans and atmosphere and living things, and eventually arranged into the precise configuration that is you. You are a temporary arrangement of ancient stardust, and tonight you are resting. Sound is a mechanical wave, a compression and expansion of a medium, traveling through matter by pushing molecules together and pulling them apart. In the vacuum of space, where there is effectively no matter between objects, sound cannot propagate. There are no molecules to compress. There is nothing for the wave to travel through. The universe's vast distances are not merely quiet, they are silent in a way that has no analogue in ordinary human experience, a silence so complete that no instrument or being could detect even a whisper from across the void. This means that the violence of the cosmos, the supernovae, the colliding neutron stars, the black holes consuming gas, is entirely inaudible to anyone outside its immediate vicinity. The explosions that outshine galaxies make no sound at all across the distances of space. What reaches us instead is light, electromagnetic waves which do not need a medium to travel. The universe communicates across its distances in light. Its language is electromagnetic, not acoustic. And so the night sky, for all its drama, is profoundly, absolutely, completely still. Mercury, the innermost planet of our solar system, orbits the Sun at an average distance of only 36 million miles, less than half the distance of Earth's orbit, and it moves quickly, completing its entire journey around the Sun in just 88 Earth days. For context, by the time a single Earth year has passed, Mercury has completed more than 4 full orbits and is beginning its 5th. Its proximity to the Sun also means it experiences extraordinary temperature swings. The side facing the Sun reaches temperatures of about 800 degrees Fahrenheit, while the side in darkness drops to negative 290 degrees Fahrenheit. Mercury has no significant atmosphere to moderate these extremes or distribute heat around the planet. Despite being closest to the Sun, Mercury is not the hottest planet. That distinction belongs to Venus, whose thick carbon dioxide atmosphere creates a runaway greenhouse effect far more effective at trapping heat. Mercury is simply the fastest, a small, cratered world rushing around its star in its brief, unceasing orbit, completing 4 full years in the time it takes the Earth to complete one. Our Sun contains 99.86% of all the mass in the solar system. Everything else, the 8 planets and their moons, the dwarf planets, the asteroid belt, the Kuiper belt objects, the comets, the dust, the gas, the scattered debris of 4 billion years of solar system history, makes up only 0.14% of the total. Jupiter, the largest planet and more than twice the mass of all the other planets combined, accounts for most of that remaining 0.14%. Earth, by comparison, is an almost infinitesimally small contributor to the solar system's total mass inventory. The Sun's gravitational dominance is what holds the solar system together. Without it, the planets would drift away into interstellar space in a matter of years. The Sun is not just the source of light and warmth for this solar system. It is the gravitational anchor of the entire structure, the massive center around which everything else moves in its patient and orderly dance. Every orbit, every tidal force, every comet's path curving back from the outer reaches, all of it is a response to the gravity of that single luminous sphere at the center of our local universe. The Moon is not a geologically dead world. Despite its silence and apparent stillness, it experiences moonquakes, seismic events that can last for hours, caused by several different mechanisms. The most powerful moonquakes originate from deep within the lunar interior, possibly driven by processes not yet fully understood. Shallower moonquakes, closer to the surface, are believed to be caused by the thermal contraction of the Moon's crust as it cools during the 2-week-long lunar night. And tidal moonquakes are driven by the gravitational pull of Earth, which slightly deforms the Moon as it moves through its orbit, flexing the interior and generating seismic activity. The Apollo missions left seismometers on the lunar surface, which recorded moonquakes from 1969 to 1977. Interestingly, moonquakes can last much longer than typical earthquakes on Earth, sometimes an hour or more, because the Moon's crust is dry and cold and more rigid, causing seismic waves to reverberate for much longer before dissipating. The Moon, silent from Earth, vibrates with its own quiet rhythms, responding to the pull of the world it orbits. Light exerts pressure. This is not merely a metaphor. Photons, though they have no mass, carry momentum, and when they strike a surface, they transfer a tiny amount of that momentum to the object they hit. This is radiation pressure, or light pressure, and while it is immeasurably small under ordinary conditions, it is real and measurable, and in the vacuum of space, where there is no friction and even the tiniest sustained force can build up speed over time, it becomes a viable method of propulsion. A spacecraft with an enormous, thin, reflective sail, a solar sail, can be pushed through space by the continuous pressure of sunlight, requiring no fuel, drawing on the inexhaustible stream of photons flowing outward from the Sun. Several solar sail spacecraft have already been successfully tested, including Japan's Icaros mission, which demonstrated solar sail propulsion in space in 2010. The concept is elegantly simple. The same light that warms your face on a sunny afternoon is also very gently pushing against you, and in the right conditions, that push is enough to cross the solar system. Comets are ancient travelers, small bodies of ice, rock and dust that formed in the outer solar system billions of years ago and orbit the Sun in long elliptical paths that carry them from the cold outer reaches of the solar system down into the warmth of the inner planets and back again. As a comet approaches the Sun and warms, the ice in its surface begins to sublimate, transforming directly from solid to gas, releasing dust and volatile molecules into space. This creates the comet's coma, a fuzzy, glowing envelope of gas and dust surrounding the nucleus. But the tail of a comet is not a trail left behind as it moves. A comet actually develops 2 tails, both of which always point away from the Sun, regardless of the comet's direction of travel. The dust tail is pushed back by the pressure of sunlight. The ion tail, straighter and more blue-white, is blown back by the solar wind. When a comet is moving away from the Sun, its tail actually leads the way, pointing back toward the star it just passed. The comet does not blaze a trail. It is the Sun that paints the tail, always in the direction of its own retreat. Water, that simple, extraordinary molecule of 2 hydrogen atoms and 1 oxygen atom, is not rare in the solar system. It is remarkably common. Ice exists on the Moon in permanently shadowed craters at the poles where sunlight never reaches. Mars has water ice at both poles and evidence of ancient liquid water in its geological history. The moons Europa, Enceladus, Ganymede, and Callisto all harbour subsurface oceans or significant reservoirs of liquid water. Comets are partly made of water ice, and they have been delivering it to the inner planets since the early solar system. Even asteroids contain water, locked into hydrated minerals. Water molecules have been detected in the clouds of gas between stars, in the disks of material forming around young stars, in the atmospheres of exoplanets. The universe is not hostile to water. It seems almost to prefer it. Wherever hydrogen and oxygen are present in the right conditions, water forms, and the conditions for its existence appear again and again across the cosmos. The molecule that sustains all life on Earth is scattered throughout the universe in remarkable abundance, waiting in the ice and the dark for conditions to change. In September 1977, NASA launched a spacecraft called Voyager 1 on a journey that, at the time, no one could entirely imagine would still be ongoing nearly half a century later. Voyager 1 flew past Jupiter in 1979 and Saturn in 1980, sending back the first detailed close-up images of these worlds before being redirected on a trajectory that would carry it out of the solar system entirely. In 2012, it became the first human-made object to cross into interstellar space, the vast expanse between stars, detected by the change in the nature of charged particles surrounding it. As of today, Voyager 1 is over 23 billion miles from Earth, the most distant human-made object ever created. It still carries a golden record, a disk containing sounds and images from Earth, a kind of message in a bottle cast into the cosmic ocean, chosen by a committee that included Carl Sagan. It travels in a direction where it will not encounter another star for over 40,000 years. In all the immensity of the universe, it is an almost impossibly small object. And yet it is ours, still going, still sending back signals that take over 22 hours to reach us at the speed of light. Magnetic fields are not confined to refrigerator magnets and compass needles. They permeate the universe at every scale, from the planet to the cosmic web. Earth has a magnetic field generated by the movement of molten iron in its outer core, a dynamic, shifting field that has reversed its polarity hundreds of times in Earth's history and continues to slowly drift and change. The Sun has a powerful and complex magnetic field whose tangling and reconnection drives solar flares and coronal mass ejections. Every star generates its own magnetic field. The Milky Way has a large-scale galactic magnetic field threading through the disk, aligning dust grains and shaping the paths of cosmic rays. Even the enormous filaments of the cosmic web carry faint magnetic fields, generated by turbulence in the early universe. Magnetic fields shape how stars form, how cosmic rays travel, how planetary atmospheres evolve, how energy is transported through plasmas. They are invisible and ubiquitous, woven into the structure of the universe at every level, a fundamental feature of a cosmos filled with charged particles and moving currents of matter. The estimated number of stars in the observable universe is approximately 200 sextillion, a number written as a 2 followed by 23 zeros. To give this some texture, if you tried to count these stars at the rate of 1 per second, counting every second of every minute of every hour without pause, it would take you 6 trillion years to finish, roughly 435 times the current age of the universe. And these are only the stars in the observable universe, the portion of the cosmos from which light has had time to reach us. The full universe, if it extends beyond what we can see, may contain unimaginably more. Among all of these stars, astronomers have identified that many, perhaps most, are orbited by planets. The number of planets in the observable universe is therefore larger still, possibly in the quintillions. And among all of those planets, in all of those solar systems, around all of those stars, in all of those hundreds of billions of galaxies, here is one small world, and on it, tonight, you are lying quietly, breathing, your eyes growing heavy, the universe turning slowly around you as you drift towards sleep. From every direction, at every moment, a rain of high-energy particles falls through the universe and onto Earth. Cosmic rays, the majority of them protons and atomic nuclei accelerated to extraordinary speeds by the most violent events in the cosmos. Supernova remnants, pulsars, active galactic nuclei, and possibly the shock fronts of galaxy cluster collisions. When a high-energy cosmic ray strikes Earth's upper atmosphere, it does not reach the ground intact. Instead, it collides with an atmospheric nucleus and produces a cascade of secondary particles, a shower of pions, muons, electrons, and photons that spreads outward as it descends, fanning into an enormous thin disk of particles that can cover square kilometers of Earth's surface. These secondary particles pass through your body constantly. On average, about 1 muon per square centimeter per minute is penetrating through you right now, having arrived from above at nearly the speed of light, passing through flesh and bone as if neither existed, continuing downward into the Earth and beyond. The universe is always touching you in ways you cannot feel, with the remnants of events that happened long ago in distant parts of the galaxy. When a star dies, whether in the quiet fade of a red dwarf trillions of years from now, or the violent collapse of a supernova in the present day, its light does not simply stop. The last photons emitted from its surface continue traveling outward at the speed of light, moving through space long after the star itself has gone dark. In the moments after a star dies, darkness begins to spread outward from the place where it once burned, and that darkness travels at exactly the speed of light, because darkness is simply the absence of new light being emitted. If you were watching that star from a distance when it died, you would not know immediately. You would continue to see it shining, fed by the light that left its surface minutes, hours, or even years ago, depending on how far away you were. And if you were in orbit around it, you would continue orbiting the empty space where it used to be, held by gravity that also has not yet reached you, because gravity, like light, propagates at the speed of light. Only when the expanding sphere of darkness reached you, the wavefront of the last light and the last gravitational influence, would the star disappear from your sky and release you from its invisible hold. Darkness, in this way, is not instantaneous. It has a speed, and that speed is the same as light's, 186,282 miles per second, radiating outward in silence, carrying both the absence of photons and the fading grip of gravity into the endless black. The Milky Way galaxy is not drifting through space at random. It is moving, along with the entire local group of galaxies, along with the larger Virgo supercluster, at approximately 1.3 million miles per hour in the direction of a massive gravitational concentration called the Great Attractor, located roughly 250 million light-years away in the direction of the Centaurus and Hydra constellations. The Great Attractor is an enormous overdensity of matter, a region of the universe where galaxies are packed more densely than average, creating a gravitational pull that is drawing our entire local neighborhood of the cosmos toward it. For a long time, the Great Attractor was difficult to study because it lies directly behind the densest part of the Milky Way's disk, hidden by intervening gas and dust. Modern radio and X-ray telescopes, which can peer through the obscuring material, have revealed a complex structure of galaxy clusters at the heart of this gravitational anomaly. We are, all of us, every human who has ever lived, every city ever built, the entire Earth, the Sun, the Milky Way, being pulled slowly and irresistibly towards something vast and distant that we are only beginning to understand. After everything, after the light that bends around black holes, the stars born in nebulae and dying in fire, the dark matter threading invisible through galaxies, the gravitational waves rippling through the fabric of space, the cosmic web stretching across billions of light-years, the ancient glow of the universe's oldest light, the neutron stars spinning in the dark, the expansion that has no edge and no exterior, the entropy that gives time its direction, the quantum shimmers of particles existing everywhere and nowhere at once. After all of it, we return to this, you, here, breathing, lying still in the dark. You are made of elements forged in stellar cores billions of years ago. You are warmed by the light of a 4.5 billion-year-old star. You are held to the surface of a world by gravity, in orbit around a star, in a galaxy drifting through a universe that has been expanding since before time had a direction. The cosmos is extraordinarily large and extraordinarily old, and it has been going about its business for 13.8 billion years with tremendous patience. It will continue long after tonight. There is nothing you need to hold or carry or understand right now. The universe has it. You can let go. You can rest.